next speaker is Barry Levine. He is a professor of chemistry at Oklahoma State University in Stillwater, Oklahoma. The title of his presentation, and I love these long ones, Improving Investigating Lead Information and Evidential Significance Assessment for Automotive Paint by Development of Pattern Recognition-Based Library Search Techniques.
I wish to acknowledge Scott Ryland for helping me formulate the title. This presentation is about the PDQ database, more specifically, how to extract information, more information from it using pattern recognition techniques. The PDQ database contains information about the physical attributes, chemical composition, and infrared spectrum of each layer of manufacturer's paint. The PDQ database has been used to analyze paint samples from hit-and-run collisions, and this analysis has often allowed for the manufacturer, model, and year of the vehicle involved in the hit-and-run to be identified. The PDQ database was designed as a general text-based search and retrieval system. This text-based search of both physical and chemical characteristics serves as a potent pre-screen, or if I may use the term search pre-filter, to allow a more general infrared spectral search of materials that tend to be very similar to one another in their infrared spectra. And the concept of the PDQ database is to narrow the list of possible vehicles to a reasonable number of suspects, not necessarily to identify the individual vehicle. Clearly, given the success that the PDQ database has enjoyed, this concept has served them well. This presentation is about clear coats. Unfortunately, all too often now, a clear coat paint smear is the only layer of paint that's left at the crime scene where damage to a vehicle, injury, or death has occurred. And in these cases, the text-based portion of the PDQ database will not help to identify the make and model of the motor vehicle. I'm going to demonstrate to you today, using search pre-filters based on pattern recognition methods of infrared spectra of clear coats, it is possible to identify the manufacturing plant from which a clear coat paint sample recovered from a paint smear was obtained. Before I begin the presentation about our research, it is necessary for me to briefly summarize commercial infrared algorithms. Most infrared searching algorithms, at least mid-infrared, involve some type of point-by-point numerical comparison between the full spectrum and each member of the library. These algorithms suffer several drawbacks. One, they lack interpretive ability because they treat the spectrum as a set of points rather than as a collection of specific bands. Band shifting is not handled well, and bands of low intensity, which may be highly informative, simply don't count much with the overall score. There's another problem, and this was pointed out by Peter Griffiths in the early 1990s. As the size of your IR library increases, the likelihood of a match will also increase, even though the spectrum of the unknown may not be present in the library. We're going to address all these problems today through the use of search pre-filters. And I wish to make the point that the RCMP does this, but they do it through their text-based information to cull down the number of possibilities with regard to the infrared spectrum. The problem is that with clear coats, the text-based portion won't work. So we're going to develop search pre-filters based on the infrared spectrum to help cull down the number of possibilities. A search pre-filter is a quick test to spot the similar spectra, thereby avoiding a complete comparison. The idea of search pre-filters was actually formulated in the early 1970s by Thomas Eisenhower, who at the time was an analytical chemist and chairman of the chemistry department at the University of North Carolina at Chapel Hill. Pretty much most of the work that has been done on commercial algorithms has been the result of Thomas Eisenhower and his students that for one reason or another all ended up at a specific instrumentation company, Nicolay. Now, utilizing search pre-filters, we're going to show you that we can get around many of these problems. But the search pre-filters are only going to work if the information contained in them is rotated on the manufacturing plant that actually produced the paint. And I'm going to show you how we do that. We're going to take the infrared spectra from the PDQ database, and we're going to be applying the Wavelet packet transform. And we're going to be passing it through two filters, a high-pass filter and a low-pass filter. And this decomposition process will allow us to extract both the high-frequency components and low-frequency components of the signal. And we're going to be using a genetic algorithm for pattern recognition analysis, which will allow us to identify the wavelet coefficients contained in the spectra that contain information about the plant from which the clear coat paint sample was prepared. Typically, or should I say, in this particular problem, we're going to be dealing with spectra that consists of 1,944 points. Using the wavelet packet tree, each spectrum will be represented by 16,342 wavelet coefficients. We're not going to have a lot of samples. It's a horribly underdetermined data set. But using this genetic algorithm for pattern recognition that my students have developed over the years, it will be possible for us to identify the wavelet coefficients that contain information about the plant and use them to formulate a classifier for identification of a plant from a clear coat paint smear. The sample problem that I'm going to demonstrate this methodology consists of IR spectra from 6 Chrysler plants. These paint samples were produced in 1999. They were obtained from the PDQ database, and they were selected by the RCMP for analysis for us to demonstrate our proof of concept. Now, each of the 6 plants, and their abbreviations are shown, it says there are 10 paint samples. Actually, it's only at least 9 paint samples. Sorry for the mistake. Some of these plants are in Canada, some are in the United States, and one is in Mexico. NEW, that's Newark, Delaware. I remember that plant well because when I was on sabbatical at the University of Delaware in 1993, I would drive past it on my way to Aberdeen to do some work. Now, for this study, only the IR spectra of clear coats from metal substrates was considered, and 2 spectrometers were employed, a Biorad 40A or a Biorad 60 spectrometer. And we divided our data set into a training set of 88 paint samples and a validation set of 3 paint samples. The 3 paint samples were chosen by random lot. A general rule typically is 10% of your samples should be in the prediction set that's commonly used. We chose a much smaller number only because we were dealing with such a horribly underdetermined data set. And the initial focus of our study was the training set. This is a summary of the PDQ data set, or should I say the paint data set that we're going to be using to demonstrate our proof of concept. The number of samples in each plant is shown, and also the distribution of parts is shown. Roof, hood, fender, door, hatchback, trunk. Now, for pattern recognition analysis, each IR spectrum was normalized to unit length, and all spectral features were auto-scaled, such that each measurement had a mean of 0 and standard deviation of 1. We will make sure that everything counts equally in the analysis, so we don't have the problems with small peaks like commercial search algorithms do. Auto-scaling will remove any inadvertent weighting of the data that otherwise would occur due to differences in the magnitude among the measurement variables comprising the data set. It's a standard thing to do in pattern recognition studies, classification studies. Now, how we select the informative features in our data is using a genetic algorithm for pattern recognition. We're going to identify a set of features that optimize the separation of the classes in a plot of the 2 or 3 largest principal components of the data. And because principal components maximize variance, the bulk of the information encoded by these features will be about differences between the classes in the data set. So we're going to be using a genetic algorithm. Each generation, thousands of different feature subsets will be considered. Principal component plots will be generated for these different feature subsets. An algorithm based on machine learning will be used to score those plots the way your human brain would. And through successive generations, by swapping chromosomes, by recombining, we're going to be able to identify those features that contain information about the problem that we seek to solve. In this case, the manufacturing plant identity of the IR spectra from the paint sample from which it was obtained. And just to give you an idea, let's say I have this hypothetical problem. I have samples. They're represented by 10 measurements. The samples are distributed between 3 classes, class 0, class 1, class 2. And if I do a principal component plot of all 10 measurements, not terribly informative. Each sample is represented by a point in the plot. The closer the points are to one another, the more similar they are. The farther they are, the less similar they are. So here is my data set. And in this hypothetical problem, it turns out that only 5 of the features are important. The other 5 features are just noise. And what they do with regard to the principal component plot is they obscure the signal in it, at least in terms of the directions of maximum variance that we wish to identify, because they're determined in a least squares sense. And when you have random noise with regard to least squares, it will obscure the relationship that you seek to identify in your data. So if we just look at the 5 variables, and our GA would supposedly identify them and do a PC plot of them, there you get them clustering to 3 groups. So those 5 variables contain information about the class membership of the sample. This is how we're going to do it. Except, of course, we're not working with 10 measurement variables. We'll be working with a much larger number. There's lots of advantages to doing this. It includes that chance classification is going to be less of a problem because we're using principal components, and the bulk of the variance or information content about the feature subset selected will be about the pattern recognition problem of interest. And features that contain discriminatory information about a particular class membership problem are often correlated. And principal components is an excellent way of assessing the information content of correlated data. In the context of the genetic algorithm, the principal component plot that we're using as our fitness function is actually serving as an embedded information filter. Feature sets are selected based on their PC plots, and a good PC plot can only be generated using features whose variance or information is principally about class difference. So this is going to help limit our search and help cull down the number of possibilities, help the GA to identify those regions in the solution space that contain the information that we seek. And this is a block diagram of our genetic algorithm. Unfortunately, for time considerations, I don't have the opportunity to go in it. Actually, this is my favorite part of the talk. This is something that we've developed over the years, and I like to say that the first student that worked on this was an undergraduate when I used to teach at Clarkson. He was a senior thesis student, and this is what he did for his senior thesis. And we published a few papers on it, and there's an old adage, if a little is good, more is better. The reason why I have all these papers here is that once I made a presentation and I was told that by an individual in the audience, they'd never seen this in the journals before, so hence it was unimportant. Nice way of addressing that criticism for future presentations. Our first step in this study was to apply principal component analysis to the data. And for those people that do multivariate analysis, this is a very standard thing to do. We're attempting to plot our data in a new coordinate system, not using the original measurement variables, but one based on variation. And if our measurement variables are correlated, often one can find, but not always, 2 or 3 principal components that explain most of the information present in the spectral data due to because of a large number of interrelated measurement variables. This is a plot of the 2 largest principal components developed from all 1,944 wavelengths for our training set. It's not terribly informative. That is, we don't see any clustering in this PC plot on the basis of class membership. Well, we use our GA to try to identify informative features, and after 300 generations, we identify 8 wavelengths. Right now, we're still in the wavelength space. Please note the clustering that's occurring. That's not by accident. The GA looks for structure in the data. Sometimes structure can be due to an experimental artifact, but through judicious pre-processing of the data, we can mitigate this possibility. It's clear that class 5, the blues, are well separated from the others, and the 2s and the 4s are somewhat separated but overlap, as are the 3s and the, what is that? And the 6s. Please note that the 2s, the St. Louis plant, is actually distributed throughout the map in 3 distinct clusters. And this is simply a summary of what we observe. We removed the St. Louis samples from the data because there was something different about them, okay? And we then applied our pattern recognition GA again. 10 wavelengths were identified with the truncated training set, and it's pretty much the same as before, the same 3 clusters. Now, we were interested in the St. Louis data set to try to understand what was going on. Why did it cluster into 3 distinct groups? Well, when we looked at the IR spectra, we observed that each group had a distinctive IR spectrum. Group A, Group B, and Group C. All the samples in Group A have one spectrum, all the samples in Group B have another spectrum, and all the samples in Group 3 have a third type of spectrum. And this is what the spectra look like, and as you can see, they're quite different. And that was using all the features. Oh, it turns out that Group A corresponds to the SUVs in this North St. Louis plant, whereas Group B and C corresponds to the Dodge Ram trucks. And evidently, during this production year, there was a change in the formulation used for the clear coats, which is why we end up with 3 clusters, not 2. Well, in any case, just simply based, even when we remove the St. Louis samples, we're not able to do the problem very well. And one thing we conclude is that we need more powerful methods to pre-process the data. For that reason, we chose to use the Wavelet packet transform to do deconvolution, not data compression, and then use our pattern recognition GA to identify the informative wavelets. We use the double-she 12-mother wavelet, so at the 8th level of decomposition, so we have 16,362 wavelet coefficients representing each sample. Here is a plot of the 2 largest principal components of the 16362. Actually, this thing is beginning to work because you'll notice that the blues, the 5s, are actually somewhat separated now. So actually using the wavelets on their own helped. Now let's use the pattern recognition GA to identify the informative features. Using it, after 100 generations, we identified 36 wavelets that contained information about the class membership or manufacturing plant. And you can see that they're reasonably well separated. Actually, this plot's similar to the one with the wavelengths, except there's one difference, okay? We're now getting separation in those 2 clusters where before we weren't. So we got an improvement. Now what we do next is we project our unknowns onto the training set defined by the 36 wavelet coefficients and the samples in the training set. And they're indicated in red with their number. And as you can see, they're correctly classified. So it worked. What conclusions can we draw? Well, from this study, we can draw the following conclusions. Pattern recognition methods can provide additional information about the class label used to characterize IR Spectra in the PDQ database, and the wavelet packet transform, when combined with the pattern recognition GA, is able to give us the information that we seek. And search pre-filters developed from wavelet coefficients can simplify library searching. And when these search pre-filters are combined with searching algorithms that are more powerful, but also more computationally intensive than Euclidean distance, our goal then will be similarity searching. The spectra is similar, but not identical to the one in the database. That capability currently does not exist, and our goal is to develop that capability. Acknowledgements: Mark Sandercock and Tamara Hotchkins from the National Center for Forensic Services, Scott Ryland from the Florida Department of Law Enforcement. Scott played a very important role in getting this collaboration going. My own research group that's been involved in this project, of which I'm only showing some preliminary data. That's Ayuba Fasasi, who is a postdoc, and he got his degree from Peter Griffiths at the University of Idaho at Moscow, someone very knowledgeable in FTIR, good guy to have on the project. Jay Maida, actually a chemical engineering student. Colin White, Nuwan Pereira, and Nikhil Murjankar. So about 2/3 of my group right now is focused on this project. And we also now thank the National Institute of Justice for supporting this work. Thank you for your time and attention.